This unit has more material than the previous one. It will be a little more intense. It will be about product measures. And in order to define product measures, we have to start talking about product sigma algebras. So product sigma algebra will be the following. Suppose we have two spaces, omega 1 and omega 2, and some sets are, so we have omega 1 and omega 2, and some sets which are measurable in the sigma algebra of omega 1. Let's call this set here A, and some sets which are measurable in the sigma algebra of omega 2. Let's call this set B. So maybe B is like this. And it's an interval plus a bunch of points, and A is also an interval and a bunch of points. Then we can, in quotation marks, define what is called the rectangle, which would be the Cartesian product of these two sets, A and B, and this is of course a subset of the Cartesian product of omega 1 and omega 2. So it will be something that will look like this Cartesian product. And so a set of this type, it's a bit metaphoric, a set of this type is called rectangle. So it's a subset of the Cartesian product of omega 1 and omega 2, which is itself in the form of a Cartesian product of two measurable sets A and B, which are both measurable in each of these spaces. So of course, this is a very strict class of subsets of the Cartesian product. Okay? Let's think of the main example of a Cartesian product as the plane. Here's the plane as being a Cartesian product of the line and itself. So there are many sets on the plane that are very nice, and they are not necessarily of this form, Cartesian product of two things. So a set of this form, it is not a Cartesian product, but this is still a nice set. And this is how we define the product of sigma algebras. So if we take, let's introduce here the notation. If we have a class of sets and another class of sets, of subsets of different or maybe equal sample spaces, by a small abuse of notation, we use this cross here. This cross is not the Cartesian product of this family and this family. It's the collection of sets that are the Cartesian product of a set in this family with a set in this family. So this is what this cross means. So it's the family of Cartesian products of measurable subsets of each of these sample spaces. And what we take as this different cross here, this different cross, so it's a cross with a circle, that is called the product sigma algebra. So this is the product sigma algebra, and it is the sigma algebra generated by this class. Okay, for instance, this is a rectangle. It is in this class because it's the Cartesian product of an interval with another interval. This is another rectangle because it's the Cartesian product of one interval with one interval. But the union of these two is not a Cartesian product of anything. So the union of these two rectangles here is not in this set, but it is in this set because this set is bigger. This family is the sigma algebra generated by the rectangles. Now this brings us to the notion of sections. So what is section? Well, when we have the Cartesian product of two sample spaces and we have a subset of the Cartesian product, then we want to talk about the section of this set, which will be the following. The section will be, so suppose this is the first here sample space. Here we draw the second sample space, and suppose this is our set. Is this ellipses here filled in? Okay. This is just an example. So the section will be the following. We fix some x here in the domain, in the first sample space. We fix x, and now we consider this set here. So this set here, the red set, is a subset of omega 2. And if this bigger set here is called E is a subset of the Cartesian product. If E is the Cartesian product, is a subset of the Cartesian product, we denote this subset here by E subindex X. So we include X in the notation because as we change X, we are talking about different subsets. So if I pick another X here, let's call it X prime. If I pick another X, so now we're talking about a different set. We're talking about this set here on omega 2, which is not the same as this set here that we had before. So this is what this notation here is saying. E subindex X, so E before was a subset of the Cartesian product. So now E subset X is now just a subset of the second space, and it's given by, well, fixing the first coordinate in this Cartesian product to be X, and considering what are the values that the second coordinate would take if we remain on the set. And, well, analogous or identical definition will hold for taking this section in the other direction. So we have our set E here, we have our set E, and if we fix a point Y in the second space, then now we have a section which is a subset of the first space. And we denote that by EY. So this will be the definition of sections of sets. And now if we have a function f, which is defined on the Cartesian product of omega 1 cross omega 2 and takes value on a third space, whatever that space is. Well, in practice, we will most often want it to be numbers, but it can be any space. Then we can talk about also sections of the function. How will it be that we can talk about sections of the function? It will be, we draw the function. So let's draw the axis x, y, and then here we'll draw the function will be z. So we draw the graph of z equal a function f of x and y. So maybe the graph of z will be something like this. This will be a surface. And when we fix the value of x, here let me fix the value of x, this will determine a cross-section of this function here. Okay? What is this cross-section? It is, as we vary y, we are getting z equals f of x and y. But now y is the argument of this function and x has been fixed. And because x has been fixed, we can we remove it in the notation. We remove it from here and we put it in the underline here to make it clear that x has been fixed and this is now a function that depends only on y. And likewise, if we fix the second coordinate, in order to make a distinction in the notation, we put it as a superscript instead of a subscript, just to say y is fixed, and I'm looking at this function as a function of x only. So I fixed a value of y, and I'm looking at now this curve here, which will be a function of just the first coordinate. You may have noticed in the previous definition that we didn't make any assumption about the function f or the set E that was a subset of the Cartesian product. They could have been any function, any subset. Now we are adding assumptions here. We are adding the assumption that E is measurable with respect to this product sigma algebra. And this important lemma here that we'll use in the upcoming video lectures. So it says if a set E is immeasurable with respect to the product sigma algebra. So you can think here's my first space, here's my second space, and we take any set here. The set can look like this. Then when we take a section, so we fix X and we consider now this little set here, okay, this set here, which would be a subset of the second sample space. We call this EX, okay, to denote that it depends on the value of X that we have fixed. So the lemma is saying if this belongs, so this product sigma algebra, F1 cross F2, which, as we have already discussed, is different from the set of rectangles. It's much larger, in fact, because it will be, if we want, it will be the sigma algebra of this set. It's generated by this family. So if my set E is my set E, if my set E is in this product sigma algebra, then for every value of X that we take here, that we fix, every value of X that we fix will give us a section which is measurable. So this is what the lemma is saying. This is a key fact. It's a very important fact. In the property, you'll see it being used in upcoming lectures. And now the second property, it is the following. Before we had this function f that was a function that depends on both coordinates of two different sample spaces. Okay, so we had the graph of this function. Well, the graph is just for the picture. You see the formal definitions, they don't make explicit reference to the picture. The picture is just to help us visualize what's happening. And it says, now that we defined what is the section of a function, we can make a claim about the property of this object, which will be the following. If the function is measurable, well, measurable with respect to this sigma algebra on the domain, so the function is from this product, Cartesian product. If it's measurable with respect to this product sigma algebra, then for each x that we fix, so here we fixed some value of x, and we looked at this function here, there's a function of one variable only. This becomes fx, x has been fixed, and it's a function from omega 2 to whatever space. This f was originally taking values. This function will be measurable for every x. So this is what the second part of this lemma is stating.